Formal language automata are mathematical models used to analyze and understand formal languages, which are sets of strings or sequences of symbols that follow specific rules and patterns. These automata are a foundational concept in theoretical computer science and automata theory. There are several types of formal language automata, each with varying levels of computational power and suited to different types of languages. Some of the most common types include finite automata. Finite automata are the simplest type and are used to recognize regular languages. They consist of a finite set of states and transitions between these states based on input symbol. Finite automata can recognize patterns like regular expressions. Non-deterministic finite automata. In-Fay and phase are a variation of finite automata where multiple transitions can be taken from a state for a given input symbol. They are often used in pattern matching and text processing. Push-down automata, PDAY. Push-down automata can recognize context-free languages and are equipped with a stack, which allows them to handle nested structures in languages like programming code. Turing machines. Turing machines are the most powerful type of automata and can recognize context-sensitive and recursively enumerable languages. They have an infinite tape and a read-write head, allowing them to simulate the computational processes of modern computers. Formal language automata serve several important purposes. Recognizing and generating languages. Automata can be used to determine whether a given string belongs to a particular language or generate valid strings in that language. Compiler design. Automata theory plays a crucial role in the design of compilers and interpreters for programming languages. Lexical analysis and parsing are two key areas where automata are employed. Parsing and syntax analysis. Automata are used for parsing natural and artificial languages to understand their grammatical structure. This is essential in fields like natural language processing and compiler construction. Theoretical computer science. Automata theory forms the basis for studying the limits of computation and the classification of formal languages based on their complexity and expressiveness. In summary, formal language automata provide a structured and mathematical approach to studying the behavior of formal languages. They are essential tools in the analysis and design of computer systems, programming languages, and various applications in computer science and linguistics. Regular languages and automata. Finite automata and regular expressions are tightly connected to regular languages. Regular languages are those that can be recognized by finite automata, and regular expressions are used to represent these languages concisely. They are widely used in tasks like pattern matching, text processing, and lexical analysis. Context-free grammars. Context-free grammars are another way to describe context-free languages. They are employed in the specification of programming languages, document markup languages like HTML, and the generation of syntactically correct sentences in natural language processing. Context-free grammars and push-down automata are closely linked. Parsing in compilers. In compiler construction, parsing is a crucial step that ensures the source code adheres to the syntax of the programming language. L-parsers and L-parsers and L-parsers are examples of parsing techniques that employ finite automata to process the syntax of the language. Practical applications. Beyond theoretical computer science, formal language automata find practical applications in data validation, e.g. regular expressions for input validation, network protocol specification, and text searching and information retrieval systems. Language processing tools. There are various tools and software libraries that implement automata and grammars. For example, Lex and Yacc are tools for lexical analysis and parsing, respectively. They're commonly used to generate parsers for programming languages. Automata simulation. Automata can be implemented in software and hardware to simulate or perform specific tasks. For instance, regular expression engines in programming languages use finite automata to search for patterns in text efficiently. Learning and teaching. Formal language automata serve as a foundational topic in computer science education. They are used to introduce students to the theoretical aspects of computation and the structure of formal languages, helping them understand fundamental concepts. Combining automata. In practical applications, it's common to combine different types of automata. For example, regular expressions can be transformed into finite automata, and finite automata can be used to pre-process input before applying more complex parsing techniques. In essence, formal language automata are versatile tools that bridge the gap between theoretical computer science and practical applications. They help us define and understand the structure of languages, design efficient parsing algorithms, and solve a wide range of problems related to pattern recognition, text processing, and computation. A deterministic finite automaton DeFi is a mathematical model used in automata theory and theoretical computer science. It is a type of finite automaton, which means it has a finite number of states and transitions between those states based on input symbols. DAFAs are particularly used to recognize and process regular languages, which are a class of formal languages characterized by their simplicity and regularity. Here are the key characteristics and components of a DeFi. States. A DeFi has a finite set of states represented by circles in the graphical depiction of the autoction of the automaton. Each state represents a particular condition or configuration of the machine. Transitions. There are directed arrows between states, called transitions. Transitions are labeled with specific input symbols from an alphabet. When the DeFi processes an input symbol, it moves from its current state to another state according to the transition labeled with that symbol. Start state. One state is designated as the start state, from which the DeFi begins processing input. It is typically denoted by an incoming arrow with no source state. Accepting or final states. Some states are marked as accepting or final states, usually by double circles. When the DeFi reaches an accepting state after processing all input symbols, it signifies that the input string is accepted or recognized by the DeFi. Alphabet. The alphabet is the set of input symbols or characters that the DeFi can read. These symbols are used as labels on transitions and represent the set of valid inputs. State operates as follows. Starting at the initial state, the DeFi reads the input symbols one at a time. For each input symbol, it follows the corresponding transition to a new state. After processing all input symbols, if the DeFi has landed in an accepting state, it accepts the input. Otherwise, it rejects it. DAFAs are called deterministic because for a given input symbol, there is only one valid transition to the next state. This property simplifies their behavior and makes them easy to analyze. DAFAs are used in various applications, such as regular expression matching. DeFis are used to efficiently search for patterns in text by converting regular expressions into DeFi asset. Lexical analysis. In compiler construction, DeFis are employed for tokenizing or lexing the source code to break it into meaningful tokens. Network protocols. DeFis are used to specify and process network protocols and validate input data. Text search algorithms. DeFis are used in algorithms like the Aho-Korosik algorithm for fast string matching. Syntax checking. DeFis are used for basic syntax checking and parsing in various applications. In summary, deterministic finite automata, DFOS, are a fundamental concept in automata theory and are used to recognize regular languages and perform pattern matching and parsing tasks in various computer science and computational fields. They are characterized by their simplicity, determinism, and finite number of states, making them a valuable tool for text processing and language recognition. A non-deterministic finite automaton monon, INFE, is a mathematical model used in automata theory and theoretical computer science, closely related to deterministic finite automata, DFAT. Like DFAs, INFEs are used to recognize and process regular languages, which are a class of formal languages characterized by their simplicity and regularity. However, INFEs differ from DFAs in terms of their non-deterministic behavior. Here are the key characteristics and components of an NFA. States. An INFE has a finite set of states, just like a DeFi. Each state represents a particular configuration of the machine. Transitions. Similar to DeFis, there are directed arrows between states called transitions, labeled with specific input symbols from an alphabet. However, in INFAS, there can be multiple transitions with the same input symbol from a single state to various other states. Start state. As with DFOS, one state is designated as the start state, from which the NFA begins processing input. Accepting or final states. Some states are marked as accepting or final states, usually by double circles. When the NFA reaches an accepting state after processing all input symbols, it signifies that the input string is accepted or recognized by the NFA. Epsilon transitions. NFAs may also include epsilon, transitions, which are unlabeled transitions that allow the machine to change states without consuming any input symbol. This non-determinism is a distinguishing feature of NFAT. The operation of an NFA is as follows. Starting at the initial state, the NFA reads the input symbols one at a time. For each input symbol, it can follow multiple transitions simultaneously.